Hi, and welcome to another Commodore 64 repair video from Coiro. This has been a bit delayed because I actually caught the coronavirus and has been able to follow up on this video, and that means that this video is also filmed maybe a bit out of sequence, because normally I do the fault finding process and I document that, but then I go back and fix the theory where I put the scope pictures and do the theoretic illustrations and stuff. I do that about simultaneously normally, but this time I actually filmed the footage and the repair, and then it was more than a week before I was able to do some of the work with the explanations and the theory behind the fault finding and stuff. So it might be a bit not, what should I say, coherent through the video. This is the third Commodore repair in the series, and let's just get on to the work, shall we? And on this one, someone has actually written the Norwegian test sort bilde, or black picture as it would be in English. I'm not sure though, the black picture can be also, of course, the total lack of a picture. I will just take out the board from this bread bin bottom that it was fastened in, and this I actually don't get the rest of the bread bin cased for, as I got it like this. But everything else seems to be complete, the mountings, and I also have the I/O shield for the power and joystick ports on this one. But it does seems like the standoffs that keeps this fast to the bottom here is broken, several of them. I don't know if this has been taken out, but it probably has. There are a lot of sockets on this board, and some of them might have been put in after this board was completed at the factory. Yes, we can see 3 of these standoffs are broken, but there are some 3D printed kits that you can make, that you can just glue them on the bottom and you get new holes for the screws. But I'm not sure if I'm going to reuse this. If I do have a bottom that's in worse condition, or I have a top without bottom, of course I'm not going to throw it away. These boards that are produced with the heavy soldering beneath the solder mask is actually my favorite. There is almost no breakage of threads on these boards. Yeah, and on the bottom of the board we can see that there is only one component that has been soldered after this board was made, and that's actually the CPU. And the CPU is not in a socket, so that might be a factory thing, it might be a replacement, but the normal thing is to put it in a socket, and that's not done here. On the rest of the board where we see the sockets, there is no obvious place that there has been solder on this board after it was new. There are a couple of lumps here and there that might be cold soldering and might just be okay. This is also a 250407 board, but this is stated as a revision B and not revision C as the 2 other boards we have repaired so far. The logic chips that are socketed here is the 373, the 2 257s, and the 139 chip. Yeah, the 3 ROM chips are socketed. The CPU is not in a socket, but the PLA and the SID is socketed, but not the 6526 chips. Yeah, there was some soldered blobs around the power switch, and here we can see also on the top there is a blob on the power switch. But I think we are just going to measure the voltages and start from there. And here is something I've actually never seen before. They have tampered with the fuse with putting a thin wire threaded around the fuse and into the fuse socket. So they actually tried to make their own fuse instead of making it obvious with putting in some silver paper or some other blob. This could easily get unnoticed if I haven't inspected this now. So the first order of the day is putting in a new original fuse. And this fuse should be 1.5 amps slow blowing. And before we forget, let's mark this board with the number 3 so we don't confuse it with the others. Yes, and now with the fuse replaced, I'm going to take up the tin cover on top of the VIC-II chip to see that we actually have something in there before we start applying some voltage. And here you can see they have actually removed this cover before. You can see there are some disturbance in the thermal grease on top of the VIC-II chip. So this has been removed before and might have been swapped. Maybe it's just reseated, but at least someone has been in here before. I will clean up this chip and put on a heat sink before we progress any further with this. And we do have to measure around the VIC chip anyway when there is a black screen. I just take a quick overview of the chips before I connect power. We have one MOS chip here, the 7408. And we have, yeah, pretty much standard chips everywhere. And we have the same memory chips all over, Mitsubishi. And we have one more MOS chip on the 7406. Yeah, but let's connect some power and see what we have to deal with here to confirm the red marker diagnosis that was black screen. And actually here when we connected power we get no signal. And that's not the same as a black screen. It means that we have no detectable video signal into our monitor. So we just start with measuring some voltages, and I put my fluke scope meter into DC voltage mode, and we just start measuring out the voltages. First we take the internal voltage regulators, and plus 12 volt looks okay. And so does the 5 volt rail that goes to the inside the tin can. Yeah, and the 5 volt from the power brick, I can measure this here on the 373, and it also looks okay. Yeah, and so does it on the 139 and the 257 chip. And if we also measure this on the user port, then we are sure that the 5 volt is spread around the board. There can of course be individual chips without 5 volt supply, but that we have to measure when we do further fault finding. So it's okay in the user port, so then we go on to look with the scope. On the previous 2 videos I used the blue LED, but the blue LED it's not showing good on camera, so I'm going to use the green one to indicate power this time. And then I fire up the trusty Regal scope, and I just probe around for the normal signals, the clock, the AEC, the read-write signal, the data bus, the address lines and so on. And instead of showing you exactly where I probe here, I'm going to jump straight ahead to the results, and I will show you what I got where. And just to get that confusion out of the way, the reason I'm not using the dead test cartridge first this time is that we have no video signal, so even though the cartridge should try to put out something, it won't show on the screen because there is absolutely no video going out from the VIC chip, it seems. Yes, and this is actually what we measured when we started to measure. I started with measuring out the video signal on pin 4 on the AV port on the back of the C64. And this goes into the TV modulator, but it actually made from these signals here the color and the SLUM signals that comes from pin 14 and 15 on the VIC-II chip. And as we can see, this video signal was all low, and the SLUM signal, that's the main basis for the composite video signal, is also low, and there are just some noise on top of the color signal, and this can be bad triggering of the scope or some real noise. There is at least no information that is normal regarding the video signal. So we do know that there is something wrong coming out of this VIC-II chip, but we don't know if it is the chip itself or if this some surrounding electronics that causes this. Yeah, the next step, that is usually the first step, is that I actually measure out the VIC-II clock on the CPU on pin 39, and that actually looks quite nice. It's how it's supposed to look. And the next signal I measure out on the CPU is the AEC, or CAAC, that is should be on pin 5 of the CPU. And I have this table that I showed you last time. This is the different places on the PCB where the AEC signal also should be. And as we can see here, the 6510 should have this on pin 5. And this is actually the combined AEC signal that is combined with the DMA from the cartridge port. Yeah, and as you can see here, this is actually measured all the same on the VIC-II chip as it did on the CPU. And that might not be a fault on the VIC-II chip. It can be some circuit here or some trace or something that is pulling this low, so that the VIC-II chip can't deliver the signal it's supposed to deliver out on this pin. As you can see, this Moose chip was R3 revision, and this is before I cleaned it and put on the heatsink. And here I measured the different clocks on the VIC-II chip, and that actually looks quite good. This is the phase 0 clock, and you have the phase in clock that should be half of the crystal oscillator, and you have the pin 21 that actually is the same frequency as the crystal oscillator. This is also the clock that is fed into the pin 1, the clock input on the 6510 CPU. So the 6569 actually appears to be ticking in some way, and the VIC-II chip is, as we know, also responsible for the memory refresh cycles, and this is actually controlled by this RAS-CAS decoding here on pin 18 and 19. They seems to be working quite okay. They have the correct pulses. I don't remember the exact pulse width and frequency and so on, but it appears to be ticking on 2 MHz, and that should be okay. This is also measurable on pin 4 and pin 15 on each of the memory chips, and it seems okay. So the DRAM circuit in the VIC-II chip is also ticking. Yeah, and the memory chips, while we're looking at them, we are also going to look at the data lines to see that there is no stuck data line that keeps something from triggering or something from booting that's necessary for the VIC-II chip to actually do its thing. As we can see, all the data lines appears okay. And I did not measure them on the CPU this time. I did measure them on pin 2 on the memory chips. And as you can see here, pin 2 is the same as pin 14. I forgot to mention this last time, but the data inputs and data outputs, or D and Q as they are often called, is connected together on the C64. On some computers where the memory refresh is handled differently, these can be separated. And yeah, there's a lot of examples of that actually. And I also make this small table that you could see which data line it is on which CPU. That's not always self-explanatory. So everything seems to be ticking okay on every part, except that we are not getting the AAC signal out of the VIC-II chip. To test that, I am actually going to put the VIC-II chip into my SixtyClone and see if it behaves exactly the same in the SixtyClone as it does in this machine. So that will be my next step. Yes, and here we break out the SixtyClone, and we are just going to test the VIC-II chip. And we just do the simple test. If this gives us no signal and no video output, we just replace the VIC-II chip and work over from there. Yeah, and as we can see, there is no video signal at all out on this too, so we are just going to replace the VIC-II chip with the one that we used on our first board. Yes, so now we know that the VIC-II chip was confirmed dead in the SixtyClone. It behaved exactly the same, and it did seem to be working on every level except that it didn't handle the AEC signal. So this is moot, that's for sure. And this is actually the hardest part to source new on shelf. I have been able to source CPUs, room chips, PLAs, and also 6526 chips, but VIC-II chips, especially the European variant and not the NTSC version, it's difficult to find. So PAL VIC-II chips, they're starting to get really rare. And as it seems that the projects to make a clone of this is actually halted, we need to preserve as many as these as we can. And I'm very reluctant to buy these off eBay because I know that for every VIC-II chip I buy off Romania or Czechoslovakia or Poland or someone else, there is a dead 64, so it's make really no sense that I take one from a machine that might be in a better shape than the one I'm repairing, and I just kill that one to get a new one. But for the rest of the test, we use another VIC-II chip, and we use the VIC-II from the first board we repaired. So after I put on a heatsink on this one, they actually look exactly the same. Both are R3 versions. Yes, and now we just couple up our board again, and we replace the VIC-II chip. And we are going to probe out all the signals to see if this actually works. And we are just going easy on the signals that we already know works on this board. And we are going to concentrate on the signals that we don't know at all if working. And that's primarily the AEC signal. As before, I'm going to present all the measured results when we go through them afterwards in an orderly fashion. When we replaced the VIC-II chip, we actually had a real black screen, and that is that we have the video sync out on pin 4 that works as it should, and we have the AEC signal on pin 16 on the VIC-II chip as we should. But the issue with the combined AEC on pin 5 on the 6510 CPU, that actually remained exactly the same. So this is a low level that we measure on this pin. So the VIC-II chip is now doing what it should, but something is going amiss from the AEC here and to the combined AEC that should go into here. And that is a lot of copper in between, and there is also a chip that combines this signal, as we shall see. So now we just ask ourselves what the cack is going on. The AEC on the VIC-II chip is just working fine. And as we can see, it goes straight to pin 4 and is also measured fine on pin 4 on the 74 LS08. And the DMA signal that comes straight from pin 13 on the cartridge port. And this is also input on pin 2 on the same U27. I think that's the RDI signal or something. I have to look that up. And we do get output low on the CAC signal that goes to the CPU. And this pin 6 here and pin 5 on the CPU measures exactly the same. So we do now have quite the good idea of what's going wrong. So, did you see it? Did you see what actually is wrong, at least with this part of the circuit? And what might that be, you might ask, and is exactly the keyword here. This is the truth table for an AND gate. And here I've put in the DMA and the AEC signal, and the result that should be the combined AEC. On a normal truth table, this would be an A, B, and a Y or something. And as we can see here, this is actually what we have, because the DMA is kept high. So these are the situations that we actually will have here. And then we see this is an AND gate, and that means that the pin 4 here actually should control the output, because if this is 0, 1 and 0 is 0, and if this is 1, is a high pulse here, 1 and 1 should output 1. So here we actually have something that's not okay, and this is something we can deduct with simple measuring. We are not going to desolder and make some hasty repairs on this. We are actually going to think this through before we start desoldering chips. But we can see here that this gate is not working as it should, but it still can be other things that's wrong, because this input can be forced low by something else. But I don't think that is the case. And on our board we saw that the CPU actually was repaired or changed at some point, and it can be the CPU that is dragging this to a low level, but that we don't know for sure. And if you look into the schematics for this, there actually are some confusion, because on most schematics for the C64 you actually have this situation here. Yes, I'm going to move my talking head here, actually like so that you should not, can actually make it just like so. So what you see up in here is that you actually have a OR gate that's inverted on both the output, that's an NOR gate, not OR, and you have inverted inputs on these. And that makes no sense at all, because it's still stated that this is a 74 LS08. So what Commodore has been thinking here, I don't know, but this makes no sense at all that you should use this signal. But logically, this actually works, because an inverted input NOR gate is exactly the same as an AND gate, as we will see here in the truth table. Because if I have the NOT AEC, instead of 0, I will get a 1. And I normally have the NOT DMA, and I put in the DMA. When I OR that, I will get a 1. And when I invert this, I will get a 0. And the same here. I will get a 1 inverted to 0, and 1 and 1, and inverted to 0 again. And 0, 0, 0 actually makes a 1 when that's inverted. So you can see here, this line here exactly matches this when you invert the inputs on the OR gate. As it actually is an AND gate that is used, and that is also described in the schematics, this makes no sense at all. But there are some schematics out there that actually picture this right. So this is how it should be. And of course there also are some more confusions regarding this. And a bubble pictured like this is an inverter. And some people might be thrown off track because of that, because it's not normal to show this as an inverted input like so on a normal gate. And the IEC signal also uses the bubble like so, but that's actually not the defined standard. The standard is actually showing this to be this triangle on the output. So there is a lot of confusion because these symbols are not the same everywhere. But this symbol is normally a square with an AND symbol inside and an inverted output. So this is an not AND or NAND gate. Have this symbol or this symbol. So, but this is the pinout of the actually 74 LS08 chip. And as we can see here, we have pin 4, 5 is the inputs and pin 6 are the output, like it's pictured here. So at this point, our main theory is that something inside the 74 LS08 AND gate is pushing the output towards 0 or towards the negative.
I think we better replace the negative power coupling.
So we choose to desolder the 74 LS08, both because it's the cheaper chip and also it's the most likely candidate for failure. But if this is okay, the 6510 is next out. Yeah, it seems that the chip is still stuck, so we need to use our hot air gun to desolder it the last bit and ease it out of the holes on the easiest way. And less chance to damage the PCB. Yeah, then we have to just solder in a new socket, and here we have used one of the good sockets with the round holes. And when the socket is soldered in and secure, we just put in a new 74 LS08 chip and we are ready to test the system again. First without any cartridge and anything, just to see if there is a picture on the screen. Yes, and then it was the moment of truth. Does it work? Will it boot up to our familiar blue screen? Yes, and it would. So it seems that this is working, but we have to do a throughout test with a complete test harness in place to check that things actually is working as it should. For the test to complete successfully, we also have to supply the board with at least semi-working SID chip that at least has the analog XY inputs. Yeah, and here we can see that it's testing bad on on both 6526s. I'm not sure if that is right. I think I will try to reseat all the connectors on the test harness and do another test. It might be that the contacts are a bit corroded, and yeah, I think we do that. Yes, and then the tests went straight through, so we now have another fully working Commodore 64. Yes, and now we are going to look at the truth and nothing about the truth table for this Moose 7712 that also goes under the nickname 7408 or 74LS08. And when I just take an auto find, it can't find the chip because it's not recognized with any known truth table as functioning. And when I look up the chip here to the right and actually do a test on that chip with the defined truth table, we can actually see some faults here. On our chip, it was pin 4 and 5 that should give an output 6. And here you can see the fault condition that we actually detected here. So that's why I never cut off the legs and other things when I do desoldering of these chips. If I keep the chip intact, I can actually test it afterwards to check that I actually changed the right part. And I think that's really important. But this part, even if it has been good, would not have been reusable because on these boards, and especially these boards with the good soldering mask with a lot of tin beneath the mask, all the legs on the chips that's used in this have the cut off legs, so they much shorter. I don't know if that's something that's everywhere, but at least most of the boards I have seen have these short legs. And these short legs, you can actually make them work in good sockets, but mostly I won't trust these chips with the short legs in a socket, because I know at some point it will pop out. Yes, one small step for Coiro, but hopefully one big step for those that comes after me, that they will know that this board actually was fully working as of today. Yeah, I'm just doing a small test here to see if I can capture the sound from this pole position cartridge, because I do have some trouble now sampling sound on my capturing device. Yeah, and still no sound. I have to fix that. Yes, so that's it for the third video in this series. And this time we repaired this board. And as you might have noticed, when we fixed these boards, we are not leaving every of the major chips behind in these boards. So that we can say at these boards that we have fixed, they are totally okay, but they will lack some of the system chips. And I can of course order up and fill out these boards with chips, but I won't do that. Maybe if I get to sell them or give them away, I will fill them out. But on this board, it's just a VIC-II chip that is missing, and this is my test SID chip. It's fully working, but it has one of the filters is kind of bad. So that's it for this video. Hope you enjoyed the content, and this was one of the more methodic error finding processes that I have in this video, where we first tackled the VIC-II chip and then the 74 LS08 that was bad. So thanks for watching. Hope to see you again in the next episode in this series, and the next episode will be C64 with keyboard and case, and not a board that I has lying around. And that video will be in about 1.5 weeks. Please hit like and subscribe if you want to be notified when we post new videos. So see you in the next one.